When I graph tangent and cotangent functions, I like to have the equation in this format, where you have the b value with the x inside the parentheses. But as we'll see in this video, as we extract data from the graph to create an equation, we're going to use this format. We're going to get our b value and we're going to place that as the GCF. The other thing that's different about going from equation to graph versus graph to equation is how to determine the phase shift. When I graph from an equation, what I like to do is take whatever's in the parentheses and set that equal to 0. To get the starting point of the tangent function, which I consider the first vertical asymptote. Then, once I get my I solve for x, and that gives me my phase shift. That gives me the starting point. That gives me the first vertical asymptote. Then I figure out the period of this transformed function, and I add that to get the second vertical asymptote, the end of the tangent function. Then I split this in two to get the middle. I split it in two again to get my quarter points, and I have my 5 critical points. Starting point, first quarter point, middle point, and the third quarter point. With the tangent and cotangent graphs, it doesn't work that way. With a tangent graph, you have to use the middle to determine your phase shift. In other words, the graph they give you, let's say this is at negative pi over 3, you don't use that as your starting point and work backwards. With the tangent graph, you use the center. That is going to be your C value right there. Now, when you're doing cotangent, you're going to use the vertical asymptote on the graph. Okay, so let me go backwards here. If this was a cotangent function, we don't use the center to get the phase shift. We use the first vertical asymptote. And the reason it's different for cotangent and tangent, when you go from the graph and you're creating an equation, I believe, I'm not 100% sure, but I believe it has to do with this. The fact that when you transform a point, you take the x value divided by b, and then you apply the phase shift. The y value really isn't an issue here. So look at this. The tangent graph starts with the center at x equals 0. If x equals 0 here, and you divide it by b, this is going to be 0. This is a pure phase shift calculation. Look at cotangent. That starts at x equals 0. The vertical asymptote is at x equals 0. If you're trying to go from the graph of the cotangent backwards and create the equation, that x value is 0. Again, it's a pure phase shift calculation. So in summary, when you're given the graph and you're trying to determine the phase shift and you're dealing with a tangent, you want to look at that center point, what's happened to it. When you're dealing with the graph of a cotangent and you're trying to work backwards to get the equation, you look at how the first vertical asymptote has been shifted, and that'll give you your phase shift. Let's go to our first example. These numbers here were hard to read, so I went ahead and wrote in the x and y values of all the critical points. Now, because this function is increasing as we move left to right, we're going to consider this the tangent function. Now, as I mentioned, when we create the equation from the graph, I like it in this format, where the b has been pulled out as a GCF. For some reason, if you don't do it that way, it just doesn't work out. Okay, first let's find the middle of the graph and the amplitudes. Okay, so look at the middle of the graph. The middle of the graph has been elevated 2, 3. And by middle, I'm talking about in terms of the y direction. So the fact that the normal tangent graph sits on the x-axis, and this has been lifted up by 3, we know that our d value is plus 3. Now, to get our a value, we look at the distance between these quarter points and the middle. And you could see that that's a distance of 2. So our amplitude is going to be 2. Okay, now we're getting into the more difficult part. It's the x values. The phase shift, and the horizontal stretch or shrink. Okay, so here we go. Let's first get the period. So the period of this transformed function goes from -4 to 8. That's a total of 12 radians. So the period of this transformed function is 12. Now recall, when we're given the equation and we try to find the period, we take the pi value, put it over b, and that gets us the new period of the transformed function. Here, we know that the period of the transformed function, the function we're given, is 12. So we're going to work backwards to get the b using this formula. So whenever we're in this situation, we could simply switch these values. So we're going to end up with pi over 12 as our b value. And again, that pi over 12 is going to sit there as a GCF. Okay, now let's look at our phase shift. As mentioned previously, you do not look at the vertical asymptote and say that the phase shift is 4 in the left direction. If you do that, you're going to get the wrong equation. You got to use the center of the tangent graph. So you could see that our center has been moved. And normally the tangent graph center, the x value starts at 0. It's been moved 2 to the right. So we know that we're going to have x minus 2 inside the parentheses. Okay, folks, so our final equation written over here in green is going to be y equals 2 tangent bracket pi over 12 times x minus 2 plus 3. Now, we also could use, if we want, we could use this distance here. So everything could stay the same, except we can call this a phase shift of 14 to the right, and we can replace that 2 with a 14. But everything else would stay the same, including the position of the pi over 12 as the GCF. So this equation would give us the same exact graph. Sorry, that plus 3 has been off the screen. Folks, let's take this same graph and write an equation for cotangent. So as you know, the cotangent normally decreases. This is an increasing graph, so that means we're going to do a reflection by adding a negative. Now, most everything stays the same. The only thing that's going to change is the phase shift. So the negative is going to, I'm sorry, that should be cotangent. So the negative in front, the cotangent, pi over 12, and now the phase shift is going to change because we are not going to be looking at the center point like we did with the tangent. We're going to look at the vertical asymptote. So you could see the vertical asymptote moved 4 in the left direction. The cotangent first vertical asymptote is usually at 0. So a movement of 4 in the left direction is going to manifest in a positive 4 inside the parentheses, but everything else stays the same. Okay, folks, let's go ahead and look at Desmos here. So this is our first graph here that we use with the tangent function, and you'll see everything lines up. You see our centers at 2, 3. Our first critical point is at negative 1 comma 1. Here's our center at 2 comma 3. First critical point, negative 1 comma 1. We see a vertical asymptote at 4, vertical asymptote at 4. Okay, now let's look at changing the equations a little bit. Okay, we said before that we can also consider this a shift, negative 14 in the tangent direction. So if I go ahead and click on that, you could see it overlaps with our original graph. It just changes from red to purple. And then here's the equation for our cotangent version with the negative and with a +4 as the phase shift. And you could see the graph just changes from blue to black, indicating that these three equations will result in the same exact graph. In our next graph, we see that it is a decreasing graph, so let's try to find a cotangent equation that fits this graph. Again, we're going to fill in our data points with the b pulled out as a GCF. Incidentally, folks, when we get our final answer with the b as a GCF, if your teacher mandates that you distribute that b through the equation, go ahead and do it after you get it in this version. In other words, don't start out like this. Get your data points and plug it in as is. Do it this way. Start by plugging in your data points with the b as a GCF, and then at the very end, go ahead and distribute. Otherwise, you'll get the wrong equation. Okay, so here we go. Let's first find out what's going on with our y values. Here we see that the normal cotangent graph, the middle sits on the x-axis. It's been elevated by 3. So we know our d value is going to be +3. Now we're going to look at the distance between the center point and our quarter point maximum. So we have here a distance of 2. That's going to be our amplitude. Now, we're going to find our b value. Remember, the original period, which is pi for both tangent and cotangent, divided by the b value gives you the period of this transformed function. And you could see this transformed function has a period of 4 pi. Two ways to do that. You could see our first vertical asymptote is at pi. Our second one is at 5 pi. You could simply count 1, 2, 3, 4. Or you could say 5 pi minus pi is 4 pi. In any event, we're going to put 4 pi as our period of this transformed functions. We're simply going to switch the b with the 4 pi, and we will get a b value equal to 1/4. So I'm going to go ahead and place that in as our b value. Now, recall, when you're looking at the phase shift for the cotangent, you look at the first vertical asymptote. And that is because on the cotangent function, that's an x equals 0 value. Okay. With tangent, in the problem we just did before, we looked at the center. But here, we're going to look at the first vertical asymptote. We see that it's been shifted pi in this direction to the right. So we're going to put that as x minus pi. So our equation is going to be y equals 2 cotangent 1/4 x minus pi plus 3. Okay, you could also do the same equation. Everything stays the same except make that x minus 5 pi to get the next portion of the tangent graph. These will be the same graph. Let's take this same graph and write it in terms of tangent. Recall, tangent is normally an increasing function. This is decreasing, so we're going to have to add a negative. We're going to put a negative in front. The other difference when you move to tangent is you do not look at the first vertical asymptote. to determine the phase shift. Rather, you look at the center point. You could see the center point has been moved from its normal value at x equals 0, 3 pi units to the right. Or we could use this second period, or second period of the tangent, and consider this a transformation 7 pi units to the right. So both those versions are listed here. Here, this would be 3 pi to the right. That would be this first graph, and this is 7 pi to the right. Okay, folks, let's go to Desmos and look at how we did. So here's our original cotangent graph here. Trust me that the center was at 3 pi comma 3, and now we're going to change it. We're going to change it to a minus 5 pi for the cotangent. That would be the first vertical asymptote here. And if we do that, we see the original function turns from red to black. So it's the same as exact function. Here we switch to tangent. We put a negative in front of it. Now we looked at the center. We saw that the center could either be considered a 3 pi move to the right or a 7 pi move to the right. And as you'll see in a moment, if we click this one, our original cotangent graph goes from black to blue. And then if we this one, the graph goes from blue to green. These are all the same graphs going all the way back to our original red cotangent function. Next, we are given this graph and we want to work backwards and create the equation. Again, in our equation, we're going to have that b value pulled out as a GCF. So I think the best thing here is to identify what's the underlying sinusoid, and then we'll be able to determine whether we're going to use cosecant or secant. So I think the first thing we should do is go ahead and put little points here, because we know our sinusoidal graph is going to hit these vertices. Next, let's determine the middle of this transformed function. So we can see this is a point at y equals 10. Here we're at y equals negative 2. That total distance between negative 2 and 10 is 12. We divide that by 2 and it's 6. So if we come down 6 y value units from 10, we're going to be at a y value of 4. And that's going to be our horizontal midline of the sinusoidal function. Okay, the next thing we want to determine is where does the sinusoid cross the middle? And that's going to be the same location as the vertical asymptotes on this secant slash cosecant graph. So you could see we have a vertical asymptote here at x equals 2. That means we're going to have a point hitting the middle there. There's another vertical asymptote at x equals 4, another one at x equals 6, and finally another one at x equals 8, and there's also one here at x equals 0. So folks, we have our sinusoid. Let's go ahead and draw it in and then determine whether it's going to be easier to use our cosine or sine graph. Okay, to me it looks like we should use sine graph. We have a middle point here. It moves up just like the sine graph does. Okay, so because we're using sine, that means this is going to be a cosecant graph. Okay, our a value is going to be our amplitude. That's between here at y equals 4 to y equals 10. That amplitude is going to be 6. So we're going to have 6 cosecant. Okay, let's get our d value. Our d value is going to be this distance here. From normally at y equals 0 to y equals 4, it's a vertical shift up of 4 units. Okay, now let's get our b value. To get our b value, we need the period of this transformed function. So here, if that's our starting point at x equals 2, it goes all the way to x equals 6. That's a period of 4 for this transformed function. To get our b value, we're going to use the normal period of 2 pi for a sinusoidal function divided by b equals 4. We're going to switch the b and the 4, and we're going to end up with a b value of pi over 2. Okay, finally, we're going to look at our phase shift, and just like with the tangent and cotangent functions, what we look at is going to be unique dependent on which graph we're using. So if we're using the sine graph, recall the sine graph, the parent sine graph starts at x equals 0 at the middle. So that's what we're going to use here. So normally that would be at 0. We could see it's been shifted to the right 2 units. That's going to manifest in a minus 2 inside the parentheses. Or we could take that center value as the first, as the phase shift, and we could say x minus 6. So everything else would stay the same, except x minus 6 would be placed where x minus 2 is located. Finally, let's see if we can interpret this sinusoid as a cosine function, and that will allow us to write this as a secant graph. So if we consider this a cosine function, the starting point would correspond to where the parent cosine function is x equals 0. So the cosine parent function at x equals 0 is going to have a high point at that level. So let's look here. This is the sinusoid graph. So we have a high point here at x equals -1, a high point here at x equals 3, and a high point here at x equals +7. Okay, so when we're rewriting this as a secant graph in deference to an underlying cosine graph, everything is going to stay the same except for the phase shift. Whereas the sine, we use that middle point. The cosine, we're going to be using this high point as the way to determine our phase shifts. So everything's going to stay the same. And of note, you do not put a negative in there like we did with the transition from tangent to cotangent. Okay, so here, everything else is going to stay the same except for what's in that parentheses. So here, if we consider that our high point with -1, we can make that +1. Or we can consider x equals 3 a high point and change that to x minus 3. And finally, we could consider x equals 7 as the high point and change that to x minus 7. Next, we are asked to write the equation of the graph shown. So here, this looks like a tangent graph. It is rising, namely increasing as we move left to right. So the first step is to find the middle of the graph. So we see that it runs from -4 pi over 3 to 2 pi over 3. Let's just focus on the numerator. Let's forget the denominator for a second, then we'll bring that in at the end. So this graph runs from -4 pi all the way to 2 pi. That's a total of 6 pi. Let's divide that in 2. That's 3 pi, and then add that to -4. So -4 plus 3 is going to be -1 pi, and then we bring the 3 back in, and that gives us our center. Now let's find our quarter points. The lower quarter point is going to be between the blue dot and the first vertical asymptote. Again, ignoring the 3 in the denominator. From -4 to -1, that is 3 steps. 1, 2, 3. Let's cut that in half and make it 1.5. So we are going to go 1.5 from the blue dot. So if that's -1, we want to go to -2.5. So that's going to put us right here in terms of our x value and there in terms of our y value. So that's going to be -2.5 pi over 3. and that would be negative 3 pi over 3, otherwise known as pi. Okay, continuing on, let's now find the upper quarter point. It's going to be halfway between negative 1 and 2. Again, this is 3 steps. We're going to cut that in half. It's 1.5. This time, let's go back 1.5 from 2, and that puts us at 0.5 pi over 3. Okay, so we can use these decimals. If your teacher wanted you to change it to fractions, well, we could just change this 0.5 to 1/2. So that would be 1/2 pi over 3. Multiply top and bottom by 2, and that would give us pi over 6. Here, instead of negative 2.5, we could have negative 5 over 2 pi over 3. Again, multiply top and bottom by 2, and that would give us negative 5 pi over 6. But let's just leave the decimals for simplicity because we are writing equations here. And let's erase all this. Okay. Now we are set up to extract some data and apply it into our proposed equation. Again, we are using tangent, so we're going to have a times tangent. Again, when you build equations, you have to pull, in my opinion, you have to pull the b out as a greatest common factor. Okay, let's first look at what this information tells us. This tells us that the tangent graph has been lifted by 2 units, therefore our d value is going to be positive 2. Now, in terms of the amplitude, that's going to be the distance between this point and the middle and that point in the middle. So to me, the y value of this looks like 2.5. That looks like 1.5. That means I believe this is an a value of 0.5, otherwise known as 1/2. Okay, now the more difficult challenge is inside these brackets. Okay, let's get our b value. To do that, let's look at the period of the graph they give us. So it goes from negative 4 pi to 2 pi. That's a total of 6 pi over 3, otherwise known as 2 pi. Okay, this is 4 pi over 3 and another 2 pi over 3, 6 pi over 3, otherwise known as 2 pi. So the period of this transformed function equals 2 pi. So the way we get our b value is the period of the parent function divided by the b value gives us the period of this transformed function. We're allowed to switch these. We're going to have pi over 2 pi equals b. Therefore, b equals 1/2. Okay, now finally, let's get our phase shift. For tangent, remember, we're going to look at the center point. So it looks like that tangent has been moved negative pi over 3 to the left. That's going to manifest in us calling this x plus pi over 3. Okay, our final equation written in green up here, and let's do it down here at the bottom. Y equals 1/2 tangent of 1/2 as the GCF, x plus pi over 3 plus vertical shift of 2. And again, if your teacher mandates that you present this in the distributed form, now you distribute the 1/2. You do not put that 1/2 next to the x in the original. In other words, this is not the equation 1/2 x plus pi over 3. If you write it like that, you're going to get it wrong. You have to first put it in the format with the b pulled out, the x and the phase shift together, then distribute the x. So this would really be 1/2 pi over 6 if in fact your teacher mandated in this format. Next, let's explore how to write this graph as a cotangent graph. Remember, the first thing we do with a cotangent graph is add a negative. That flips this from an ascending or increasing function to a decreasing function. And folks, everything else is going to stay the same except for the phase shift. The phase shift, the focus is now going to switch to the first vertical asymptote. Everything else stays the same. Look, the A value stays the same except for the addition of the negative sign. The B value stays the same. The D value, vertical shift, is no change. Okay, to get the phase shift, the horizontal shift for a cotangent, wait a minute, that should be cotangent, sorry. To get the phase shift, to get the horizontal shift of the cotangent graph, we focus on the vertical at first vertical asymptote, because on the parent function that was at 0. That x equals 0 means this is a pure phase shift analysis. Okay, so look what happened. This got shifted negative 4 pi over 3 to the left. That means we're going to place 4 pi over 3 as our C value. Okay, let's now go to Desmos and evaluate how we did. Okay, so let's start with this purple function here. This is the equation we came up with, and you have to trust me that that vertical asymptote, negative 4 pi over 3, 2 pi over 3, the center at negative pi over 3, that this matches. And then we came down here and we gave the cotangent form. We added a negative and we changed the shift to emphasize the vertical asymptote. Vertical asymptote is 4 pi over 3 to the left. We're going to manifest that with a plus sign. And let's see, if I hit this button, will that purple turn to this color? And it does. So purple goes to green. I take green away. We got purple, green. It's the same exact graph.